Hello friends, welcome to my lecture on review of integral transforms 2. First we shall look at an application of Laplace transforms to heat conduction equation. In the last lecture we had discussed Laplace transforms. Here is an example on the application of Laplace transform to heat conduction equation. We are going to determine the flow of heat in a semi infinite solid x greater than 0 when initially the solid is at 0 temperature, and at t equal to 0 the boundary x equal to 0 is raised to a temperature u naught and maintained at u naught. So, let us assume that u x t denotes the temperature distribution in the semi infinite solid at a distance x from one end. Suppose this is your one dimensional var. Okay, so this is your end x equal to 0. We have an element here x at a distance x from x equal to 0 at time t. So, we want to determine u x t. U x t is the temperature in the var at a distance x. Let me say this is end A and at time t. So, we have to solve the first order second order differential equation c square u x x, that is c square del square u over del x square equal to delta u over delta t. Now, we are we have to determine the temperature distribution u x t in the var. Here we are given the initial condition at t equal to 0, the solid is at 0 temperature. So, we are given u x 0 equal to 0 for all x. Okay. At time t equal to 0 the temperature is 0 and the boundary condition is that x equal to 0 is raised to a temperature u naught and maintained at u naught. So, u 0 t is equal to u naught for all the time t. Okay. So, this is initial condition, this is initial condition, and we have this as a boundary condition. Now, in order to solve this differential equation, what we do is we multiply by e to the power minus s t on both the sides of this equation and integrate over the interval 0 to infinity. So, what we have c square integral 0 to infinity e to the power minus s t equal to this. Okay. Now, since we are integrating with respect to t, x and t are independent variables, so I can also write it as now here this is a product of two functions of t. So, let us integrate by parts. So, e to the power minus s t into the integral of delta u by delta t, which is u x t minus integral 0 to infinity derivative of e to the power minus s t is minus s now. Let us say that Laplace transform of u x t is u var x s. Okay. So, let us say this is Laplace transform of u x t. So, we will have here c square, this u bar, okay, equal to u bar, this u bar, and then here we will have as t goes to infinity u x t, okay, e to the power minus s t when t goes to infinity goes to 0, Okay, when s is positive, so u x t into e to power minus s t goes to 0 because u x t remains finite. So this goes to 0, and when t equal to 0, what we get? This is e to the power 1, this is u x 0. So minus u x 0 plus s times integral 0 to infinity e to power minus s t u x t dt, which is the function u r x s. So we get s u r. Now we are given that u x 0 equal to 0, so this is equal to s u r. So what we have? Thus we have this one. Okay, or we can say it can be regarded as an ordinary differential equation of second order, where we are where the variable is s, and we are keeping x as constant. So this is of the form auxiliary equation will be m square minus s by c square equal to 0 if we regard it as ordinary differential equation of second order. So then m is equal to plus minus root s by c. Okay, so we have u r x s. U r x s will be some constant which will depend on x into e to the power x root s by c plus b times e to the power minus x root s by c. Now when x goes to infinity, we must take a equal to 0 in order that this u r does not become infinite. Okay, so to keep u r finite, okay, as x tends to infinity, okay, we must take a equal to 0, so that temperature remains finite. Okay, so what we have? U r x s equal to b times e to the power minus x root s by c. Now let us put x equal to 0. X equal to 0 means, putting x equal to 0, we get u r 0 s equal to b, and now let us find u r 0 s. So we have u 0 t equal to u naught. Here you put, this is your Laplace transform, u r x s equal to integral 0 to infinity e to power minus s t u x t dt. So put x equal to 0 in this, so we get u r 0 s equal to integral 0 to infinity e to the power minus s t u 0 t dt. Okay, u 0 t is u naught. So this is u naught times, u naught is a constant, so integral 0 to infinity e to the power minus s t dt. Okay, and this is u naught times e to the power minus s t over minus s 0 to infinity. So if s is positive, then as t goes to infinity, this will go to 0. So we will get u naught by s, u naught by s. So we get b equal to u naught by s, and therefore what we have? So b equal to u naught by s, and hence u bar x s, u bar x s is equal to u naught by s into e to the power minus x root s divided by c. Okay, so we get this. So we get u bar x s equal to u naught by s into e to the power minus x root s divided by c. Now let us take the inverse Laplace transform of this. So L inverse of u bar x s equal to u naught into L inverse of e to the power minus x root s divided by c over s. Okay. Now, in the last lecture we had found inverse Laplace transform of e to the power minus b root s by s equal to 1 minus error function of b over 2 times root x. So, let us apply this result. This result we had seen, we had proved using the inversion formula for the Laplace transform, and so this we can use, and this will give you. And now let us note that u r x s is equal to Laplace transform of u x t. So, L inverse of u r x s will be equal to u x t, and therefore, this will give you u x t equal to u naught. Okay. Now, let us compare here. We have root s into minus b is replaced by x over c. Here we will put instead of t x, because here we had the function of x. So, we have this is equal to 1 minus error function of, in place of b will put x over c. So, we will have x over 2 root c, x over 2 c root t. Okay. Inverse Laplace transform when we take u x t using this formula will give us this. So, this is the solution to the heat equation by using the Laplace transform. Now, let us consider a Fourier series. Let f be a periodic function of period 2 pi, which can be represented by a trigonometric series f x equal to a naught by 2 plus sigma k n equal to 1 to infinity a n cos n x plus b n sin n x. If term by term of this series is allowed, term by term integration is allowed, then we obtain the so called Euler formula. You can see that because we have 1 cos x, sin x, cos 2x, sin 2x, they are all orthogonal functions over the interval minus pi to pi. Okay. That means, if you take any pair of these two functions over the interval minus pi to pi, their product you take and integrate over minus pi to pi, then it is integral is always 0. So, what we have from this equation, when you multiply this by cos m x, when you multiply the equation 1 by cos m x and integrate over the interval minus pi to pi, then what will you will get, a m will survive, n will be equal to m, then only we will get non-zero value here, otherwise it is all 0. So, we get a k, a m we get, and a m is arbitrary. So, we get a k equal to 1 over pi minus pi to pi f x cos k x dx. This includes this a naught also. So, we have k equal to 0, 1, 2 and so on, and these b n's are given by this formula, b k equal to 1 over pi minus pi to pi f x sin k x dx. Now, we note that because of the periodicity of the integrands, you can see f x is 2 pi periodic, cos k x is 2 pi periodic. So, f x cos k x is 2 pi periodic, and here f x into sin k x is 2 pi periodic. So, the interval of integration can be changed from minus pi to pi to any interval of length 2 pi. For example, we can take the interval 0 to 2 pi. So, because of the periodicity, the interval of integration can be replaced by any other interval of length 2 pi. For instance, 0 less than or equal to x less than 2 pi less than or equal to 2 pi. Now, if f is continuous or merely piecewise continuous, by piecewise continuity we mean continuous except for finitely many jumps in the interval of integration. The integrals in 2 will exist. These integrals can be evaluated, and hence we may compute the values of a k and b k, and then form this trigonometric series a naught by 2 plus a 1 cos x, b 1 sin x and so on. This series is then called the Fourier series of f, and its coefficients a k's and b k's are called the Fourier coefficients of f. Now, the following theorem gives sufficient conditions for the representation of a function by a Fourier series. Now, let us look at the question of the convergence of this Fourier series. When this Fourier series converges, and if it converges, whether it represents the function f x or not. So, this theorem gives us sufficient conditions for the convergence of the Fourier series. If a periodic function f x with period 2 pi is piecewise continuous in the interval minus pi to pi and has a left and right hand derivative at each point of that interval, then the corresponding Fourier series 3 with coefficients 2 is convergent. This series is convergent and its coefficients are given by these formulas. These formulas are called as Euler's formulas. Its sum is f x. So, the sum of the series will be f x at each point of continuity of f, and at a point of discontinuity its sum will be equal to the average of left hand and right hand limits. So, at the point x naught. So, f x naught plus f x naught minus divided by 2. So, these conditions are known as Dirichlet conditions, and almost every function with of f x of period 2 pi can be represented by Fourier series that we come across in applications. So, consider the function f x equal to minus k when minus pi less than x less than 0, and f x equal to k when 0 less than x less than pi. Now, let us see the graph of this function. See, minus pi to 0, it is minus k. Let us take k positive. So, we can write like, we draw the graph like this, and then from 0 to pi it is k. Okay, so, and then it is extended 2 pi periodicity by 2 pi periodicity. Like this. So, you can see that this is an odd function, okay. F x is an odd function here. That is f minus x is equal to minus of f x. We can see that. So, if you look at the Euler's formulas, from the Euler's formula for a k, a naught is equal to 1 over pi minus pi to pi f x dx. Since f x is an odd function, integral over minus pi to pi f x dx will be 0. So, a naught is equal to 0, and then the value of a n is equal to 1 over pi minus pi to pi f x cos n x dx. Since f is an odd function, cos n x is an even function, so their product is an odd function, and therefore, this integral is also 0, and this is 0 for all n equal to 1, 2, 3 and so on. So, let us now look at the formula for Bn. Bn equal to 1 over pi integral over minus pi to pi f x sin n x dx. So, here f x is an odd function, sin n x is an odd function, so their product is even. So, I can write it 2 over pi 0 to pi f x into sin n x dx. Now, over the interval 0 to pi f x is equal to minus k, f x equal to k. So, we can write it as 2 k over pi, k is a constant, I can write outside 0 to pi sin n x dx, and this will be equal to 2 k over pi integral of sin n x will be minus cos n x divided by n. So, 0 to pi, so we will get 2 k over pi 1 minus cos n pi divided by n, and this is therefore equal to 2 k over pi 1 minus 1 to the power n divided by n. So, this is equal to, if n is even, this will be 1 minus 1, so 0 if n is an even integer, and this will be equal to 2 if n is odd. So, we get 4 k over n pi when n is odd integer. Okay. So, we can write now the Fourier series for the function f. Fourier series is a naught by 2 plus sigma n equal to 1 to infinity a n cos n x plus b n sin n x. So, this is given by a naught is 0, a n's are zeros. So, sigma n equal to 1 to infinity b n sin n x. B n is equal to 4k over n pi when n is odd integer. So, replacing n by 2m minus 1, take n equal to 2m minus 1. Okay. So, then m will take values 1, 2, 3 and so on. So, we will get sigma m equal to 1 to infinity b 2m minus 1, that is 4k upon 2m minus 1 into pi sin 2m minus 1 into x, or I can write it as 4 over 4k over pi, because that 4k over pi is a constant. Sigma n equal to 1 to infinity sin 2n minus 1 into x divided by 2n minus 1. This is the Fourier series for the function f, and its sum is equal to f x over the points of continuities, and at the point of discontinuity is the average of left hand and right hand limits. So, the Fourier series of f is given by this for minus pi less than x less than 0, because f is continuous here, and 0 less than x less than pi where also a function is continuous. The discontinuity points you can see in the interval minus pi to pi, the discontinuities occur at minus pi, 0 and pi. So, the sum of the series here is the average of left hand and right hand limits of f x. Now, let us look at a particular case. Suppose I take x equal to pi by 2. At x equal to pi by 2, what do we notice? At x equal to pi by 2, function is continuous and takes value k. Okay. So, since function is continuous, f x will be equal to this series. Okay. So, we will have f pi by 2 will be equal to 4k over pi, sigma k equal to 1 to infinity sin, this will be sigma, instead of k here it should be n. So, n it should be. So, sigma k n equal to 1 to infinity sin 2n minus 1 into pi by 2 over 2n minus 1. So, then what you see is that f pi by 2 is equal to k. So, k equal to 4k over pi sigma n equal to 1 to infinity sin 2n minus 1 into pi by 2 divided by 2n minus 1. This k will cancel with k, and we will have sigma n equal to 1 to infinity sin 2n minus 1 into pi by 2 divided by 2n minus 1 equal to pi over 4. Okay. And sin 2n minus 1 into pi by 2 is equal to sigma n equal to 1 to infinity minus 1 to the power n minus 1 divided by 2n minus 1. So, this is equal to 5 by 4. So, we get 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on equal to pi by 4. So, by using the Fourier series, we can also find the sum of series of constant terms in some particular cases. Now, let us discuss Fourier series of functions having arbitrary period. In applications, periodic functions rarely have period 2 pi. Therefore, in order to find the Fourier series of a periodic function f t with period say t, we use the change of scale. We introduce a new variable x such that f t as a function of x has period 2 pi. Let us define t equal to t over 2 pi into x. Then when x will take values plus minus pi, t will take values plus minus t by 2. So, f t is equal to f t over 2 pi into x, which is a function of x, let us call it as phi x, then becomes a 2 pi periodic function. We can easily check that phi x plus 2 pi is equal to f of t over 2 pi x plus 2 pi, and this is equal to f t x upon 2 pi plus t. Since f is periodic with period t, this will be equal to f of T x upon 2 pi, and which is equal to phi x. So, phi is a periodic function with period 2 pi, and so we can find the Euler's formulas for the function phi. Write the phi, by writing the Euler's formulas for the function phi, we can determine the coefficients of the Fourier series for the function phi. A k equal to 1 over pi minus pi to pi phi x cos k x dx, k equal to 0, 1, 2 and so on, and b k equal to 1 over pi minus pi to pi phi x sin k x dx, k equal to 1, 2 and so on. Now, here a k is equal to, let us put the value of, let us replace phi x by f t over 2 pi x, okay. Then we will get f a k equal to 1 over pi minus pi to pi f t over 2 pi x cos k x dx, k equal to 0, 1, 2 and so on, and here a k b k equal to 1 over pi minus pi to pi f t over 2 pi x sin k x dx, k equal to 1, 2 and so on. Now, since x is equal to 2 pi over t, let us put the value of x as 2 pi over t into t, then this f becomes f t. So, and sin k x, k will be t will be equal to, t is equal to x is equal to 2 pi over t into t. So, dx equal to 2 pi over t dt, and the limits of integration will change from minus pi to pi to minus t by 2 to t by 2, and we will have these formulas. A k equal to 2 over t minus t by 2 to t by 2 f t cos 2 pi k t by t dt, k equal to 0, 1, 2 and so on, b k equal to 2 over t minus t by 2 to t by 2 f t sin 2 pi k t over t dt, k equal to 1, 2 and so on. The Fourier series of f t now becomes a naught by 2 sigma k equal to 1 to infinity a n cos 2 pi n t by t plus b n sin 2 pi n t by t. The Fourier series for the function phi, which was Fourier series for the function phi is a naught by 2 plus sigma k equal to 1 to infinity a k cos n x plus b k sin this Fourier series for the function phi. So, let us put x equal to 2 pi t over t to get the Fourier series for the function f. So, a naught by 2 plus sigma k equal to 1 to infinity a k cos 2 pi here k x, and here we also k x. So, 2 pi k t over t plus b k sin 2 pi k t over t. So, we can find the Fourier series for any periodic function with period t. So, this is the Fourier series. The interval of integration here again, since f is of period t, cos 2 pi k t over t is also a period t. So, the integrand is a periodic function with period t. So, we can change the interval of integration from minus t by 2 to t by 2 to any interval of length t, say for example 0 to t. So, in place of minus t by 2 to t by 2, we can also write integral over 0 to t in the Euler's formulas for f t. Now, let us say for example, we have this function 0 minus 2 less than t less than minus 1, k when minus 1 less than t less than 1, 0 when 1 less than t less than 2. Let us draw the graph of this. So, here this is your minus 1 minus 2. So, from minus 2 to minus 1 the function is 0, and when minus 1 to 1 it takes value of k, and from 1 to 2 also it is 0, this one. Okay. So, you can see here, and then t is equal to 4. Okay. So, it is a periodic function with period 4 f t plus 4 equal to f t, that is given to us. So, if you look at the graph of this function over minus 2 to 2, we see that the function f is an even function. And when f is an even function, if you look at the Euler's formula for Bn is equal to 1 over pi integral over minus pi to pi this is in the case of pi 2 pi periodic function, but we have a t periodic function. So, Bn we have to write as 2 over t minus t by 2 to t by 2 f t sin 2 pi k t over t. So, let us use this formula. Okay. So, let us use Bn equal to 2 over t minus t by 2 to t by 2, okay, 2 over t minus t by 2 t by 2 f t sin 2 pi and t by t dt. Let us use this formula for Bn. Why I am writing this formula for Bn? First, because you will see that Bn is equal to 0 for all n. Since f is an even function and sin 2 pi n t by t is an odd function, so the product is an odd function here, therefore, its integral over minus t by 2 to t by 2 will be 0. So, this is 0 for all n. So, we need to calculate only a naught and a n. A naught equal to 2 over t minus t by 2 to t by 2 f t dt. So, t is equal to 4. So, 2 over 4 minus t by 2 t by 2 this is minus 2 to 2 f t dt. Since f is an even function, I can write it as 2 times 0 to 2. So, that means 4 over 4 0 to 2 f t dt, and then this is equal to 4 by 4 is 1. So, we can get now integral 0 to 1 f t dt plus integral over 1 to 2 f t dt. Integral over 0 to 1, f is equal to k. So, we have integral over 0 to 1 k dt. So, this is k, and integral over 1 to 2 f t is 0. So, we have 0. So, a naught is equal to k, and similarly we can find a n equal to 2 over t minus t by 2 to t by 2 f t cos 2 pi and t divided by t dt, and this is again t equal to 4. So, 2 by 4 and integral is over minus 2 to 2 f t cos 2 pi and t divided by t dt, t is equal to 4 dt. Okay. F is an even function, cosine is also an even function. So, we get integral over minus 2 to 2 is 2 times 0 to 2. So, we get 4 over 4 integral over 0 to 2 f t cos 2 pi and t over 4 dt. Over 0 to 1 function is over 0 to 1 function is 1, function is k. So, we and over 1 to 2 function is 0. So, we can write integral over 0 to 1 k times cos pi and t by 2 dt, and this is k times sin pi and t by 2 upon n pi by 2, and integral over the limits are 0 to 1. So, we get when t equal to 0 sin pi n t by 2 is 0, but when t is equal to 1 we get sin pi n t by 2 sin pi n by 2. So, we get 2k over n pi sin n pi by 2. Okay. So, sin n pi by 2 sin n pi. So, when n is equal to 1 we get sin pi by 2. So, this is equal to 2k over pi. When n is equal to 2 sin pi is 0. So, this is 0 when n is even. Okay. And when n is odd, say 1, 3, 5, 7, okay, but we will get sin 3 pi by 2 is minus 1. So, minus 1 to the power n minus 1 when n is odd, or this is multiplied by 2k over pi, 2k over pi n pi. Okay. So, what we get here f t, Fourier series of f t is a naught by 2 plus sigma n equal to 1 to infinity a n cos 2 pi n t by t plus Bn sin 2 pi n t divided by t. Okay. So, Bn equal to 0, A naught is equal to k. So, we get k by 2, and then you put the value of An from here, you get this cosine series. So, f t, because f is an even function, so f t, the Fourier series of f is even. Now, let us consider Fourier series of even and odd functions, which we have already seen. Fourier series of an even function, as we have seen, is a Fourier cosine series, A naught by 2 plus sigma k equal n equal to 1 to infinity a n cos 2 pi n t by t, with a n is given by 2 by t minus t by 2 to t by 2 f t cos 2 pi n t by t dt, and taking values 0, 1, 2 and so on. The Fourier series of an odd function of an odd function f t of period t is a Fourier sine series, sigma n equal to 1 to infinity b n sine 2 pi n t by t, as we have seen earlier. So, where b n's are given by 2 over t minus t by 2 to t by 2 f t sine 2 pi n t by t dt, and taking values 1, 2 and so on. The Fourier coefficients of a sum f 1 plus f 2 are the sums of the Fourier coefficients of f 1 and f 2. It is very easy to see. Suppose the Fourier series of f 1 plus f 2 is a naught by 2 plus sigma n equal to 1 to infinity a n cos 2 pi n t divided by t. Let us assume that f 1 plus f 2 is a periodic function with period t, plus b n sin 2 pi n t divided by t. So, here a n's and b n's, a n is a Fourier coefficient, a naught, let us begin with a naught is equal to 2 over t minus t by 2 to t by 2, and then f 1 plus f 2 dt. So, we can write it as 2 by t integral over minus t by 2 to t by 2 f 1 t dt plus 2 by 2 to integral minus t by 2 to t by 2 f 2 t dt. So, the Fourier coefficient a naught for the function f 1 plus f 2 is the sum of the Fourier coefficients for the function f 1 and the function f 2. Similarly, we can write a n is equal to 2 over t minus t by 2 to t by 2 f 1 plus f 2 cos 2 pi n t divided by t dt. This becomes 2 over t minus t by 2 to t by 2 f 1 t cos 2 pi n t divided by t dt plus 2 over t minus t by 2 to t by 2 f t sin 2 pi n t divided by t dt. This is Fourier Euler's formula for Euler's formula for f 1, the coefficient of cos 2 pi n t by t in the Fourier series of f 1 t, and this is the coefficient of this cos here, the coefficient of cosine terms in the Fourier series for the function f 2. So, a n is given by the sum of the Fourier coefficients for f 1 t and f 2 t, the coefficients of cosine terms. So, similarly we can show for b n's. B n's are also sums of the corresponding Fourier coefficients of sine terms in f 1 and f 2. Now, half range expansion in various physical and engineering problems, we need to find the Fourier series of a function f t, which is defined on some finite interval, say 0 less than or equal to t less than or equal to l. As it is immaterial, whatever the function may be outside the range 0 less than or equal to t less than or equal to l. So, we can extend the function to cover the interval minus l to l, so that the new function may be odd or even. The Fourier expansion of such a function of half the period therefore consists of sine or cosine terms only, because if we extend it by taking odd function, then we will get the Fourier series for the function as consisting of sine terms, and if we extend it by the even if we consider the even extension, then the Fourier series will consist of cosine terms. So, let f 1 t denote an odd periodic extension of f. Since t equal to 2l, the Fourier series of f 1 t will be given by sigma n equal to 1 to infinity b n sin to pi nt by t. Now, here t is equal to 2l. So, we get sigma n equal to 1 to infinity Bn sin pi nt by L, and Bn then is equal to 2 over L minus t by 2 to t by 2 f1 t sin 2 pi nt by t dt. T is equal to 2l. So, we can put the value of t, we get 2 over L integral over. Now, this f1 t is an odd function, sin is an odd function, product is even. So, we can write it as sin pi nt by L, and this will be 0 to L. So, here we will have 4 over L 0 to L f t sin pi nt by L dt, and here in the case of an even periodic extension f1 t of f t will, f1 t is even, cos sin is even. So, this will be 4 over t, and 4 over t means this will be t is equal to 2L. So, we will get 2 over L 0 to t f t cos pi nt by L dt, and the Fourier series is given by a naught by 2 sigma n equal to 1 to infinity a n cos n pi t over L. The Fourier series 6 and 7 are called the Fourier half range sine and cosine series of f. For example, if you take f t equal to t 0 to 0 less than t less than 2, then the half range sine series of f. Okay. So, for getting the half range sine series, we consider an odd periodic extension of f t, and when we consider an odd periodic extension of f t, then the Fourier series of f t will consist of only sine terms, and we can evaluate the values of Bn's by this formula, the coefficients of sin pi nt by L, L is equal to 2 here. So, sin pi nt by 2. Okay. So, the coefficients of sin pi nt by 2 can be evaluated by this formula 2 over L 0 to L f t sin pi nt by L dt, and we can easily show that f the half range sine series of f is given by this. And similarly, if we can find the half range cosine series of f. To get the half range cosine series of f, we consider an even periodic extension of f, and when we consider an even periodic extension of f, we apply this formula a n equal to 2 over L 0 to L f t cos n pi t over L dt. So, let us see how we get this. We can show one of the two. So, a n equal to 2 over L 0 to L f t cos pi n t divided by L dt. The function is defined over 0 to 2. So, L is equal to 2. So, we get 2 over 2 integral over 0 to 2 f t cos pi n t divided by L dt, and this is therefore 0 to 2, and the interval 0 to 2 f t is defined as t. So, we can write it as t cos pi n t divided by 2 dt. Now, we can integrate it by parts. Okay. So, we get t times sin pi n t by 2 into 2 over n pi 0 to 2 and then minus 0 to 2, and we get derivative of t is 1. So, 2 over n pi sin pi n t by 2 dt. Okay. So, when you put t equal to 2, we will get sin n pi. Okay. So, that will be 0. When we put 0, this is 0. So, we get minus 2 over n pi, and integral of sin n pi t by 2 is equal to 2 over n pi again and minus cos n pi t by 2, 0 to 2. Okay. So, we get minus 4 upon n square pi square, and then we get 1 minus cos n pi. When n is even, this will be 0, and when is odd, n is odd, it will be 2. Okay. So, we can calculate the Fourier cosine series for the function f. This complex form of the Fourier series of the function f, Fourier series of a periodic function f of period t is given by a naught by 2 plus sigma n equal to 1 to infinity n cos 2 pi n pi t by t, b n sin n pi t by t. Let us put cos theta equal to e to the power I theta plus e to the power minus I theta by 2, and sin theta equal to e to the power I theta minus e to the power minus I theta by 2 I. Then the equation 8, okay, can be written like this. Okay. So, let us see how we get this. We can write f t equal to a naught by 2. So, we get a naught by 2 here plus sigma n equal to 1 to infinity, and we get here a n cos 2 pi n t. A n is cos 2 pi n t by 2. So, a n e to the power I theta. Theta is 2 pi n t by t. So, 2 pi n t by t plus e raised to the power minus I 2 pi n t by t divided by 2, and then we have b n e raised to the power I times 2 pi n t divided by t plus minus e raised to the power minus I 2 pi n t divided by t over 2I. Okay. So, this is what we have, and then we collect the coefficients of e to the power 2I n pi t by t and e to the power minus 2 pi I 2I n pi t by t. Okay. We will get this form. This will be equal to a naught by 2 plus sigma n equal to 1 to infinity 1 by 2 a n. Now, 1 over I is minus I. So, minus I b n e to the power 2 pi I n t by t. Okay. And then here 1 over I is minus I. So, we will get a n plus I b n divided by 2 e to the power 2 pi I n t by t with a negative sign. Okay. So, if I write this as C n and this as minus C n, so we will get a naught by 2 plus sigma n equal to 1 to infinity. Okay. So, let me write C naught equal to a naught by 2, C n equal to a n plus I b n by 2, and C minus n equal to a n minus I b n by 2. Okay. Let us see what we have defined earlier. C naught equal to a naught by 2, C n equal to a n minus I b n by 2, and C minus n equal to a n plus I b n by 2. Let us make choice like this. So, this is a n minus, this is n minus I b n, this is a n plus I b n. Then we will get here C n e to the power minus 2 pi I n t by t, and this will be C minus n e raised to the power minus 2 pi I n t by t, and we will be able to write it as sigma n equal to minus infinity to infinity C n e raised to the power 2 pi I n t by t with this choice, where C n's are given by this expression. Okay, and takes value 0 plus minus 1 plus minus 2 and so on. Now, this is known as the complex form of the Fourier series of f. Okay. And its Fourier coefficients are given by 9. So, this is known as the complex form of the Fourier series of f, where C n's are given by this expression. This is useful in problems on electrical circuits having impressed periodic voltage. This is complex form of the Fourier series of f. So, here we need to find C n's. Okay. C n is equal to, as we have seen earlier, C n is equal to 1 over t minus t by 2 to t by 2, 1 over t minus t by 2 to t by 2, and we have f t e to the power minus 2 pi n t by t. Okay. So, 2 minus 2 pi and I n t by t. Okay. So, let us put here f now f t equal to e to power minus t, t is equal to 2. So, we get 1 over 2 minus 1 to 1. Okay. T is equal to 2 here, and f t is equal to e to power minus t. So, we get e to the power minus 2 pi I and t divided by 2 dt. Okay. So, we get here this 1 over 2, then we integrate this by parts, and when you integrate and evaluate this, you will get the value of C n. the Fourier series of complex form of the Fourier series is this one, n equal to minus infinity to infinity Cn e to the power 2I n pi t by t. So, what we do is, so Fourier this is n equal to minus infinity to infinity Cn e raised to the power 2 pi I and t by t. So, when you integrate by parts, okay, we will get this e to the power minus t and e to the power minus 2 pi I, or we can write it like this. Instead of, we can join this 1 by 2 integral over minus pi to minus 1 to 1 e to the power minus t times 2 pi I n plus 1 divided by. So, we get 2 here by 2, okay, dt, and then we can integrate. So, we get here e to the power minus t times e to the power minus t 2 pi I n plus 2 divided by 2. Okay, I can divide by 2. So, this is divided by minus 1 plus pi I n, and we put the limits minus 1 to 1. So, this is 1 by 2. Okay. When we put the limits, we get e to the power 1 plus n pi I and over minus 1 plus n pi I, and then we get plus e to the power minus 1 plus n pi I divided by minus this becomes plus. Okay. So, 1 plus n pi I, and then we simplify this, and when you simplify this, you get the representation of e to the power minus x in the Fourier series, complex form of the Fourier series. With this, I would like to end my lecture. Thank you very much for your attention.